Okay, so now, or today, or whatever, we're going to talk about functions of the degree at all but one point. What these are, this talks about functions that have holes in them, where you are able to evaluate the limit because the function is doing something pretty near the spot, but you can't actually plug in because something completely different is going on at that spot. So these are functions of the degree. At all but one point. There is a lot of algebra that's going to go into today's stuff. So if there's something specific that you use that doesn't have this name, but I'm going to write it down. So it says, let C be a real number. And f of x equal g of x for all at x equals c, then all containing c. Okay, so what this says is that you have access to two functions, f of x and g of x. They are the exact same function everywhere except at c. So let's say their f of x function looks like that. The only difference between f of x and g of x is that g of x is the exact same function, but it happens to have the hole plugged in. Okay? Well, what this allows you to say is that if you can find the g of x function, you're going to have the same limit as the f of x function, and then you can just plug the number in. Really, what this allows you to do is it allows you to take a function and basically do algebra to it until you can plug the number in. So if you initially can't plug the number in, but you can mess with it and then eventually be able to plug the number in, they're going to give you the same answer and the limits will be the same, okay? So we're going to do a few of these and just sort of talk through the algebra because people start doing some weird things when it comes to some of the algebraic stuff. they want you to find the limit as x approaches 2 of f of x. So, first thing you do is what you tried in the last set of notes, where you try to plug in 2. You can't plug in 2 because you get 0 on the bottom. Well, that's bad. So then you need to try and simplify it to see if you can find this function that's the same as f of x everywhere but at 2. So that's where you want to start simplifying it. So in terms of how you can simplify it, you can factor the top part. So if you factor the top part, it's going to factor in x plus 3 and x minus 2. These parentheses are pointless. We can put them in. What that will then allow you to do is cancel out the x minus 2 since it's a repeated function. And that gives you this new function of x plus 3. So that is your function that agrees with f of x everywhere except at one point, which is at 2. So this really is your g of x function, or whatever letter of x you want to call it. Okay? So if we wanted to, we could find the limit as x approaches 2 of g of x. So we could plug 2 into that and get 5. Okay? What that property that we wrote down initially says is that if you know that this one is 5, then that allows you to also say, this one is 5, because they're the exact same function everywhere except at 2. Okay? You don't actually need to write this part down. It's just nice to realize. The two things that they want, because they want the limit as x approaches 2 of f of x, so they want this part. They want the function that agrees with the original function everywhere except at 2. So then they also want that part. Okay? And that would be that example. Now we're going to talk about some harder algebra. Not all of it. We'll do one with some more easy factoring, but we're also going to talk about some that are pretty messy. We're going to do 3 of these. Okay, so you're dealing with a limit problem. The first thing you try to do is you try to, oh, it's like a 4, it's just an ugly minus sign, is you try to plug in 4. We attempt. We fail. So then you want to do algebra to it. Again, this one is one you're going to want to factor. So you can factor the bottom part. Then what you can do is you can get rid of the x minus 4, which was what was causing us the problem in the first place. So now I've got 1 over x plus 4. That I can plug 4 into. And then this, if you actually do the math and add instead of multiplying, would be your answer. Okay? Again, places where I'm going to get super picky. Something to notice, there shouldn't be an equal sign here. Don't randomly throw one in because you think it's a good idea. It's not. And also, until you are able to actually plug the number in, you haven't evaluated the limit yet, and you need to keep writing that limit part down. You can't do secret algebra in the corner and then come up with this out of nowhere. You need to be showing the algebra, but until you can actually plug the number in, this needs to remain a part of the problem because you haven't evaluated the limit yet. Okay, and I'm going to be super picky about that, so make sure that you're careful with that. Second one. And I used 4 again. I'm not creative when I come up with numbers. Okay, so same deal. Step 1, we attempt to plug the number in. We failed badly. Fine. So now you have to do algebra until you can plug in 4. So this one has a square root in it. When you have square roots in the problem, the easiest way to clear up the issue that you're having is to multiply the top and the bottom by the conjugate of the top part. Notice, since I'm going to put in the conjugate, which is a quantity, I put parentheses around everything. Don't not put parentheses around it, because then what happens is, number one, your work is wrong and I'll dock you. But two, it means something completely different. This and what you want to be doing is not the same thing, because this implies you're just distributing the -3 and the -4. You need to distribute the entire quantity, so you want to put parentheses around everything, okay? When you're doing that, and this is super important, only multiply out the top part. Never, 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 never multiply out the bottom part. It will always make your life worse, okay? So because they're conjugates, it's kind of like difference of squares, where you're just squaring them both. So then these two are just going to be x plus 5. Those two are just going to be -9, and the bottom doesn't change, so just write it out. Please don't try and foil that madness out and create a disaster for yourself. Okay? So x plus 5 minus 9 is really x minus 4. Notice I'm still writing this down because I haven't been able to plug in 4 yet. Watch when you do this, you don't forget to put this on the bottom. I have some people that remember to just put it on the top and then they don't have it on the bottom and it gets weird. So now you have this repeated factor, which was your problem spot, which you're now able to get rid of, which is super. So now you're looking at the limit as x approaches 4 of 1 over the square root of x plus 5 plus 3. And this you can plug 4 into. So if you plug 4 in, then you just have 1 over 6, which would be your answer. Again, this number is your answer, and this is what you're after for right now, okay? Problem, answer. Your answers generally end up being pretty nice things, okay? Even if the original problem is sort of hideous. All right, one more like this, and then a couple other things. Okay, so here you're dealing with rational functions and fractions. When you have fractions and you're trying to simplify it, first thing we're going to do is we're going to try and plug in 0. Because it's a limit problem, that's always the first thing we do. So we try. We fail miserably. So then you need to simplify it until you can plug in. So when you have fractions like that, you want to make common denominators. So if we're making common denominators here, this one is going to pick up a 5. This one is going to pick up an x plus 5, which I'm putting parentheses around so that my math is not nonsense. And then you have, writing this down because I haven't plugged in 0 yet, so I have 5 minus, and I'm going to distribute the negative over. Now here's something that I always do, and I'm going to explain why we can do it once, and then I'm just going to always do it. When you have a compound fraction like this, where you have a denominator, a common denominator, over a denominator, you can always take these two and just smash them together. For math reasons, not for fun. The reason that you're allowed to do that over here is I'd have the 5 minus x minus 5 over 5 and x plus 5 over x. Okay, so When you divide with fractions, it's the same as multiplying by the reciprocal. So the reciprocal of this x would mean I'm multiplying by 1 over x. So then you're just taking your two bottoms and smushing them together. I never write this step down. This feels pointless and like extra writing. I don't do it. If you feel uncomfortable skipping the step and you want to write this down to get here, write it down. It's always fine to show more work. You just want to make sure that if you're skipping the step, you know where it comes from. Okay, so then that's why you get to just squish those two bottoms together. I'm not going to write that anymore, but like I said, if you want to write it down, because otherwise you make it weird, write it down. So here 5 minus 5 is nothing. You have a negative x over x, which would cross out. So then you're looking at negative 1 over 5 and x plus 5. Well, this x was the reason we couldn't plug in 0 in the first place. We were able to get rid of it, which is good. So now you can just plug the 0 in. So you've got negative 1 over, this is 0. You've got 25, and then that would be your answer. Okay, so strategy for finding limits, which you can write down. You don't have to. First thing you always want to do is you want to try and plug the number in. If you can plug the number in and have it work, super. If it fails, then what you have to do is you have to do algebra to it until you can use that property that we talked about in the very beginning and plug in the number, okay? So, last thing I want to do is I want to talk about some trig limit things, and then do a couple of examples using the trig limits. We're going to pick up 2 special trig limits, which you are going to have to memorize. And then I'm going to make a second video because in regular calculus, this breaks into 2 days. In AP calculus, it's 1 day, but it doesn't make sense to redo all this in one other tiny video. So you'll have 2 videos if you're the AP people. That technically should be 1 video, and you'll have the 2 different days if you're the regular people. So, trig limits. There is something involving trig limits called squeeze theorem. What squeeze theorem says is if you are, and you can look at it if you want, it's on page 65. Squeeze theorem says that if you are looking at a function and you can't figure out how to plug in the number, if you can figure out a slightly smaller function and a slightly larger function, and you can figure out the limit of these 2 things, and they happen to be the same, then what happens is that this f of x function that's in the middle ends up having the exact same limit, and they all sort of work together, okay? You don't actually need to know the ins and outs of squeeze theorem. What's important about squeeze theorem is that it gives us these 2 special trig limits. First one is that the limit as x approaches 0 of sine of x over x equals 1. So even though you can't actually plug into that, because squeeze theorem exists, you can say this. And you can use this even though you don't have to be able to do the math behind it. Okay? Similarly, you have the limit as x approaches 0 of 1 minus cosine of x over x, and that one equals 0. So anytime either of these 2 things pop up, you just put in 1 and 0 and you're okay. So we're going to do 2 quick examples with this, and then that will be it. So looking at that first one, you are supposed to know this when you go to deal with something like this. So you know the limit of sine of x over x is 1. So then really, this 6 is like having 1/6 times the limit as x approaches 0 of sine of x over x. Well, I know that this turns into 1. 1/6 times 1 is just 1/6. Okay? That's all that goes into that. Please don't overthink it. Okay? This one is slightly harder. Now, one nice thing to notice is that these both require the limit of x to approach 0. That one's approaching paragraph 4. So neither of these are going to apply for that one. So you go, okay. So first thing you do is you try to plug the number in. So we tried, we failed. Fine. So now math needs to happen to it. So you go, okay. When you have sines, cosines, and tangents floating around, the first thing that I always do is I change my tangent into sines and cosines, because that is generally easier to deal with. Make sure when you are manipulating around trig stuff, you don't ever drop the x, okay? Don't leave it sine of blank space or cosine of blank space, because then you'll start doing weird stuff with it, okay? Put in what it actually is. So if you're looking at the top, what you have here now is you have a fraction. Well, we talked about what to do when you have fractions. When you have fractions, what you have to do is you need to make common denominators out of it. So instead of 1, you've got cosine of x over cosine of x. So then what you're looking at is cosine of x minus sine of x over cosine of x and this. So same thing. For the reasons that we talked about before, when you have the compound fractions like that, you can take the two bottoms and smush them together. Don't actually distribute them, because again, that makes things worse. Fine. Well, this and this are practically the same thing. You just have a difference of a factor of -1. So you're going to take the top and you're just going to pull the -1 out. Now this and this are the exact same thing, which is handy. So now what you're looking at is -1 over cosine of x. That I can plug pi over 4 into. So you want to plug in pi over 4. Okay. So that's going to be -1 over square root of 2 over 2. Notice, once I put in the pi over 4, you stop writing the limit part now. This is an unacceptable way to leave your answer, because you have this compound fraction going on. You need to simplify that, okay? So when you're simplifying by fractions, you need to multiply by the reciprocal. So really this is -1 times 2 over root 2. You could leave it like this. I'm not a super stickler for leaving square roots on the bottom. I don't care if you leave them there. It wouldn't help. Sometimes when it helps to get rid of them, fine. But if you left it like this, I could live with this. This, rotten. This is okay. This one technically simplifies beyond that, so I would probably keep going. But this wouldn't be wrong. If you wanted to keep going and rationalize it, then you're looking at -2 root 2 over 2. The 2's would cross out and just get negative root 2. Because this is nicer than this, I'd be tempted to simplify it, but if you don't notice it, you want to leave it like that, fine. But again, bad, fine, also fine, okay? And then that would be it. Unless you're in AP Calculus, in which case you need to continue and watch the other part, or the next video.